How many different kinds of atoms do we have if we have sampled an element? How many different kinds of atoms? We have lots of atoms, that's true. How many different kinds if it's an element?
1 to 18.
No, I mean, how many different kinds of atoms if I have a sample that's a pure element? Nope. If I have an element, so for example, this wire, it's got some crud on it, but if it was pure copper, how many kinds of elements would I have? How many kinds of atoms would I have? Just one. Copper is just one, right? If it's a pure elemental sample, I just have one element. Now, as we talked about, chemistry involves changing elements, so more than one atom together becomes what we call a molecule, all right? And then chemistry is all about how the different atoms and molecules react and change and become different things, okay? So I'm going to start something here. It's going to be a chemical reaction. It takes a little while to get going, though, so we want to give it some time. So what we have in this vial is a copper wire, okay? You forgot to remind me. Be safe.
Safety first.
This is a solution of silver nitrate. So that means there's silver atoms in here. Now, when you hear about silver, what do you normally think of?
Shiny metal.
Shiny metal, like silverware, right? Okay? You're going to see this doesn't look like shiny metal. It looks like water. Okay? It's not water. First rule in the chemistry lab, don't drink anything. Okay? So we're going to set that there for a minute, and we're going to see if something starts to happen chemically with the different atoms and molecules, all right? So silver nitrate. Silver is in solution as what we call an ion. That's another important word. Anybody know what an ion is? Anybody heard of that before? Okay, Jared.
It's like a combination of atoms, like polarization.
Not quite. Okay, let's talk about an atom. What makes up an atom? If you want to build an atom, what parts do you need? Protons, neutrons, and electrons. Okay? Chemistry is really all about electrons changing things around. Okay? So an ion is an atom that has either gained extra electrons, so it has an overall negative charge, or lost electrons, so it has an overall positive charge. Okay? And ions can dissolve in solution because they're charged. Water dissolves charged things. Water doesn't dissolve metal, generally speaking, right? But water can dissolve ions. Ions will go into solution, right? So we put some solution in there, silver ions that don't have enough electrons, and copper wire, and we're going to see what happens to that, okay? So we're going to watch that happen, then we're going to make a prediction what would happen if we put iron into a solution of copper nitrate. Now, what's one of the keys that we have that chemistry has been happening? Something that we look for. Color change?
Wow.
Well, that was just mixing of air. Okay, so it was kind of yellow. We can make it green. It's supposed to go, it's not quite.
Awkward.
Yeah, maybe I didn't give it the right stuff. So let's look at the color here. We've got kind of a bluish greenish color. Let that sit for a second. And while we're letting that sit, do something else here. I want you to tell me, so let me move this over here. Here's the thing you want to keep an eye on. Let me move this back. Everybody see this beaker okay? Stand up if you need to. We are going to pour into that beaker a clear, colorless liquid. That's kind of boring, right? Okay, clear, colorless liquid. And I'm going to pour in, you guys want to stand up. Go stand up. Another clear, colorless liquid. Now watch it and tell me when the chemistry happens. Keep an eye on it, these things can be sneaky. You guys keep watching that. Keep watching. I don't know. Keep watching. It's a little, it's winter time, it's a little cold. That does affect reactions, by the way, temperature. Yeah, I have had this not work a few times, but bottles. Huh, okay. Let's try something else. Now, watch this one. That one was so exciting.
Oh, something's happening now. No, it's not. Yes, it's not.
Okay, it is. Kind of blue. Yeah, it's kind of bluish. That's not just my coat.
I thought it was your coat.
It is slowly turning blue. It's supposed to turn really fast.
Well, I thought it was because your coat.
Well, it didn't work, so nothing's.
Maybe the chemical had expired.
Well, that happens, but. Okay, now watch that one. Okay, whoa. Wow.
That's what we were waiting for. Was that?
That's what we're waiting for, right? So we have this nice blue solution, right? A nice blue solution. What? What? Let's change it. It's blue. See? So a nice blue solution. Now this guy, notice it turned back. It changed colors. What? No, see, it's blue. And now this one's blue too, right? No, this one's blue. That one's blue. This one's still blue. Yellow. Okay, see, I'm messing with you guys. Now notice, as it changes, can you see what's happening? Does it change all at once? It's kind of going from the top down, right? It just has to do with how it got mixed. I got it to go once where I kind of had a stripe that would change. The top and bottom would be dark, and the middle would be clear or yellow, and then it would kind of swoop through. Okay? What's another indication there's a reaction happening here? There's bubbles coming off of it. Okay? So is this reaction going to go forever? Is it going to change color forever?
No.
No, why not? Does anything go on forever?
No.
Eventually things run out, okay? So we'll keep an eye on this and see how it looks when it's done. That one just didn't go. It's supposed to turn. This is supposed to go that same color as blue. It looks like it sort of tried. It got a little bit faint. Didn't quite work. Now, what's another indication that a reaction has happened? Heat. Temperature change, and in particular, you guys might want to back up a little bit. That's that thing.
Fire.
Yeah, that's another indication that a reaction happened. So in that balloon, I have hydrogen gas. Now hydrogen gas will react with oxygen in the air to make what? To make water. I'm going to make some water. Now, if you're worried about noise, don't stick your finger, cup your hand over your ear. Okay? Use the palm of your hand, don't use your fingertips. You don't want to poke your ear. Okay, just put your hands lightly over your ears. And we'll do it 3, 2, 1.
Wow. Exciting.
Okay, thank you.
Yeah. Woo! Woo-hoo. That was a good show. Yeah, where's the water at?
Okay, what's that?
Where's the water?
Where's the water? It went out of the room. We made water in this space. It's a little late. We don't really see it now. Okay.
Because it evaporated so fast. So at this point, it talked about fire.
So we saw that something happened because we saw the fire, right? Well, fire's kind of cool. It's fun to see and all, but we can actually, one of the big things that mankind has learned how to do is harness fire to do things with it. How'd you guys get down here today? The car. The car. How's the car work?
An engine that heats up gas. Gasoline.
What the heck was that?
So that's how you drive, right? you need a way to make an explosion in a confined space, and that pushes the piston of your car. This is constantly happening. Boom, 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 boom. Okay, with your car at 2,000 RPM, yeah, that's the RPM. That's one rotation, one revolution. Okay. You can find my torque here. Do you guys see any torque spots right there?
There's one up front. It's like it's underneath the thing, but yeah. If you went up front,
Okay.
yeah, you got it.
Oh, went under the, yeah, it was a small person.
I have small
You got it? Awesome. Thank you. Whoops. Okay. So that's not exactly, I mean, that's basically what's happening in your car engine. Now, let's look at this. Can we tell that something has happened?
Yes.
You see that something has happened there?
Wow.
You see that? What does it look like?
It's clean. Clean.
Remember, what did I put in there? Silver nitrate. So what's growing on the wire?
Looks like it's been
That is
snowing on it.
also silver.
I can understand that.
Okay? So let me teach you a little bit of chemistry here. When you're doing a reaction, it's important to do what's called balance the reaction. And so balance, so one of the important ideas in chemistry, can I create matter? Can I destroy matter? Can I make matter that wasn't there before? What are we doing in chemistry? We're changing it around. We're changing its form. We're changing its shape. Let me show you an example of what I mean here, okay? We can change form. We can change structure. We can drop things. Okay? We can take liquid. We can take, let's get this in blue color just so it's better. Well, there was a little plug in the gap and it fell down into the bottom. So let me give it a nice color, okay? So I just mix some color into my liquid. But now, if we give this another liquid, stir.
Oh, wow.
It goes from being a nice liquid
Turned into Metamucil.
to being goopy slime. Now, would you believe that this is about 90% water? So why is it slimy? Why is it not just flowing like water does?
More dense.
Not so much the water. There's other
It's more
molecules in there
dense.
that are kind of interacting and hanging out and making connections with each other, and that's what gives this a slimy kind of a texture. But this is mostly water. In fact, you are mostly water. By mass, you're about 70% water. Okay? So if you remember the video there, it said mostly carbon, nitrogen, hydrogen, and oxygen. By mass, you're mostly oxygen.
That's why it's so easy for you to
Minerals
cut
in your
weight.
bones, those contain a lot of oxygen, and all the water is mostly made of oxygen. So did we create any new matter here? No, we just rearranged it. We just have the molecules doing different things, but it's all the same stuff. So balancing a reaction, back to what's happening here with the copper. So we have copper metal, and we have silver ions, which don't have enough electrons. So what do you think is happening in this reaction? What do we have here that we didn't have before? We have silver metal. And it's getting kind of fuzzy, right? We have silver metal growing on the tree. How did the silver ion become silver metal?
It makes this like copper.
Not exactly, but it did take something from the copper. What did it take? It took an electron. See, this plus means it has a positive charge. It means it's missing an electron. So it stole an electron from the copper. So now what is the copper? Copper's an ion. If it's an ion, is it metal? Where did the copper go? It's into the solution. If you look carefully, you see the solution. Get away from my coat. The solution has a slightly bluish tint to it. So because from the copper. The slight bluish tint is from the copper ions. Similar to what's happening here, this is a solution of copper sulfate. So this is actually copper with a 2+. Can't write today. So we're going to take a solution of copper 2+.
Yes, don't push it by hand.
What's that?
The red center.
Yeah. And we're going to take a different metal. We're going to take iron. Who knows what the chemical symbol for iron is? Iron.
Fe.
Fe comes from Latin, ferrum.
Faith. Faith in Spanish.
So, what might happen? This is you're supposed to make. So get your paper back. You're supposed to make a prediction of what happens if we put an iron nail into a solution of copper sulfate. These are copper 2+ ions when they're in with the sulfate. We're going to put iron. So I've got a nail. Hopefully these nails work. So if they galvanize the eye of the nail, then this section won't work. So that's why they galvanize it.
Talk about the solution that's.
Copper 2+ is what's in the solution. Oh, that one? Yeah, is it done?
Oh, wow.
It's still bubbling, so it's not done. But the color has stopped changing.
Wow.
So I've got a nail, which is mostly iron. I've also got a chunk of iron. So take a look at this here real quick. You can see it's just kind of dark gray iron. Okay. We're going to put both of these into that solution. We're going to see what's going to happen. But you're supposed to make a prediction. What do you think is going to happen?
Just kind of like what happens in the wire. Instead of like the iron kind of growing, I guess, kind of like the copper.
So we make a copper growing on the iron. Okay. So the copper ions could steal some electrons from the iron. So then where's the iron going to go? The iron will be ions going into solution. That's our prediction. So write something down about that. So prediction is that we might see copper coming out onto the metal, onto the iron. And then the iron will be going into solution. Of course, we can't see the ions in solution, so the test we can do for that. So that's our prediction, okay? So I'm going to put this in here. And we're going to wait. See what happens. Okay? While we're waiting, though, there's lots of other cool stuff we can do. So our prediction is that this will go to copper metal plus iron 2+, okay? This is an idea, this is what's known in chemistry as oxidation and reduction, change in how many electrons something has, okay? And this is kind of cool, but it's not super exciting. We can do much more exciting things. We'll do in just a minute. Doing a combination of iron oxide and aluminum. So aluminum metal, okay, iron oxide, also known as what? Double click. Iron oxide is rust. So what's happening? You know, you see the pickups driving around and have the back end all rusted out, right? Brother Lloyd would never let that happen to his truck. Okay? Iron oxide. Iron reacting with what? Oxygen. Oxygen. Where is the oxygen coming from?
Air.
The air. What facilitates and mediates that reaction? Water.
Rain.
So how do we prevent that?
Paint.
Keeping it dry, keeping it covered with, like, paint.
Something
So,
hydrophobic.
copper and aluminum. What's that?
Something hydrophobic.
Yeah, paint. Keep the water off. So you keep your truck painted and waxed and whatever else. You don't want it to rust out. Aluminum and a grayish metallic powder, so you can see that as I'm pouring it into here. If we mix the aluminum with the iron, and I need to stir it up with this handy spoon here. Okay. So right now that's aluminum metal. Meaning it's got all its electrons, it's perfectly happy. But if there's going to be a reaction here, which otherwise why would I be doing this, right? What do we think might happen? Not Jared.
Make a big move.
Well, it's chemically what might happen. There's going to be a chemical reaction. There has to be some sort of change of bonding partners, right? So right now, what's attached to the iron? The oxygen. What might happen in this reaction? The oxygens might move. make aluminum oxide, and what would be left behind? Pure iron. That's our prediction. This is also a redox reaction, change in oxidation state. Okay, I need to grab something. You get this. We're actually going to use this magnesium wire as my fuse to start the reaction.
That sounds.
Turn the lights down.
You know, I think there's gonna be fire involved.
Pay no attention to the burning paper towel. That's not what matters.
Fire.
There we go. Let's see if the reaction happens.
That's cool.
What do you think? Did a reaction happen? Yeah, come on, you clap.
Yeah. Woo-hoo-hoo.
Tell me about the product of that reaction. What can you say about this?
Very hot.
How
Looks
can you
like
tell it's hot?
It's blowing.
It's blowing. Blowing things are hot. This is much hotter than your stove. This is probably when it first hit about 3,000 degrees.
wow.
Okay, but it's cooling off very
My mom
quickly.
told me not to touch
So this reaction actually, they used to use, and I think they still use, when they're putting down railroad tracks, to weld the railroad ties together.
Wow.
You put this in between, put it in the joint, and then set this off, and boom, you've got iron right in there, welded in,
Wow.
and they can smooth it off, and so drain it.
That'd be a fun job to have.
Yeah, so this is known as thermite. Very exothermic reaction. This is a lot of energy, a lot of heat. Okay, but it just made some iron for us. A bit more dramatically than what might be happening over here. So we're going to let this go. It's hard to tell if anything's happening exactly. We're going to let this go a little bit longer. Okay. But you can still see this is going, right? Look at that.
Wow.
It's still growing. It's getting really fuzzy. Okay. All right. Let's see. What are we going to do next? Let's do this next. So we have two main kinds of change that we talk about in chemistry. What are those two main kinds of change?
Chemical and physical.
Chemical and physical. What did we do just now? Was that chemical or physical? That was a chemical change. There was a change in who was attached to what? Bonding partners. Okay? Let's do something else here. Here we have a solution of what's known as sodium acetate. Ah! Work. Water? Okay. And we're going to put just a crystal in here. One crystal, actually about 3 crystals probably.
Wow.
What is happening?
Oh my goodness. Filling up a whole beaker. 3 crystals. That's expensive.
Throwing what? Throwing crystals. Okay. And the crystals are going to grow until what?
There's no more room.
It runs out of room until it fills up the whole bottle, right? Now, the interesting thing about this, sodium acetate. That was a solution of sodium acetate. It was called supersaturated. So if you're like making candy, you make a solution of sugar that's very highly saturated. When it's hot, you cool it down, it hardens up with candy. Okay. This, when you mix it in there and you get these crystals to come out, feel the bottom. What do you feel? Okay, it is kind of warm, isn't it? So they actually use these, right? They use these as hot packs.
Wrong thing.
Oh, wow. What we take on winter campouts,
Yeah.
right?
Yeah, put that in the bottom of your sleeping bag.
Put that on the bottom of your sleeping bag, right? That'll keep you warm for a while. This is actually, it sometimes gets hotter than this, depending on how correct the solution is. And they can recharge this. How do you think?
Boiling it.
Warm it back up. Put this in a pot of hot water. Get it back up. Roll it all back out. Put it back up on the shelf. You're good to go for the next time. Okay? So that's kind of cool application of some chemistry. We can release energy as heat. Now you saw that happen here. This is a little bit more controlled, okay? So it's not going too crazy. So if we can do reactions that release energy as heat, what else should we be able to do? Blow things up? Oh yeah, we've done that. But I'm talking about the way that the heat flows. Now what have I got here? I've got some crystals. I've got some other crystals. So before you saw that I mixed liquid plus liquid and I got changing color liquids. I mixed liquid and crystal, got big crystal. I mixed liquid and liquid and I got slime. Okay. Let's see what happens here if I mix crystal and crystal. Is that water? That is just water, yep. Water on this board. John, come on up here for a second.
It's thickening.
It's John.
Hello, John.
Oh.
John. Okay, I want you to tell everybody what's happening. You're the observer.
You've done this before, John.
You've seen those crystals, right? Does it look like just crystals, or what's going on in there?
It looks thicker.
Kind of slushy?
Yeah.
Okay, do you smell anything? Don't stick your face like this, it's kind of nasty. You smell anything?
Yeah.
What does it smell like?
Salt.
Sort of. Does it smell kind of like cleaner?
Yeah.
Yeah, so we're actually getting some gas coming off. Okay, go sit down, please. It's not toxic. It doesn't smell. It's ammonia gas. Doesn't smell great.
It's not toxic.
So a lot of your glass things.
Ammonia.
So we've gone from crystal plus crystal. Now it turns out some of those crystals actually had water molecules bound up in the crystal. And so as I'm stirring this, those water molecules are coming out and releasing and making this slush. And then there's a reaction happening which involves proton transfer, different from electron transfer, to turn the ammonium ions into ammonia gas. And the gas is like, ooh, we're out of here. They take off and they leave. Okay. So can we reverse this reaction like we could with that one? No. Once the gas is gone, the gas is gone. You're not getting it back in there. Okay? But this can be very useful. That worked. Okay. Just more water. Good. Yeah, a little bit more water there.
Yeah, look at this, it's cold. Yeah.
They actually use this for athletic trainers as instant cold packs.
Okay.
They have the two different compounds separated within the pouch.
I love that.
You snap it, break the seal,
Wow.
and then start kneading it together to mix it. And you've got instant cold pack that could be used if somebody sprained their ankle or whatever.
What kind of chemicals are in there?
So it's barium nitrate and a barium octahydrate, barium hydroxide octahydrate. Pretty benign stuff.
Barium?
Let's look past the parasitic book for easy. Okay. So far so good? Let me tell you a story. So here in the chemistry department, we actually have, you wouldn't believe this, a pet elephant. And our pet elephant has a problem. He really likes to eat candy. Now, if an elephant eats too much candy, what's going to happen? The elephant, no, before he gets diabetes, he's going to get cavities, right? So, have you ever seen an elephant's teeth? Elephant teeth are massive, right? They're bigger than your hand. So, what do you need if you're going to brush an elephant's teeth?
A big toothbrush.
Big toothbrush and a lot of toothpaste.
Wow!
Was that a reaction?
Yes.
How can we tell?
No, it's hot.
Steaming, so it got hot. It made a lot of bubbles, a lot of gas being generated. Okay? So some of the things we look for chemistry to see if it's happening is we look for color changes. We look for change in state. Solids that weren't there before, liquids and gases that weren't there before, making of bubbles, okay? Now it turns out this actually, the reaction was already kind of going just very, very slowly. What I added to it is what's known as a catalyst. Anybody heard that term before? What does a catalyst do? Not Jared. David.
Speeds up.
Start some, okay?
Speeds up a reaction.
It wasn't yeast in this case, but it can be done with yeast. I use potassium iodide.
Initiates it or
It makes stuff
speeds up the
happen.
reaction.
Yeah, the catalyst makes the reaction, otherwise it would be really, really slow. It makes it go faster. So it speeds up the reaction. The important thing about a catalyst is it itself is not used up in the reaction. Now here it's mixing, we're not going to get it back out again. The catalysts are not consumed in the reaction, they just make the reaction go faster. Okay, this one, I need to get going because it can take a little while to get this fully set up. This right here.
Oh, yeah, Benson.
Talked about energy conversion. Energy conversion is of course important. We talked about it for like driving up cars, right? Where else is it kind of important?
Heating your house.
Heating your house, okay? What's that?
Inside of it.
Inside of us. Why do you eat food every day?
So we get like energy.
Gives you energy, right?
Cellular respiration.
Somebody come up here. Come in here. Need you to open that door. Just guide it along the side. That will work. Just open it. Pull it. Pull it. Guide it. No, get better than this. Yep. And move it above that. There we go. Now, okay, cellular respiration. What does that mean?
Process of transferring food into energy through ATP.
Yeah, food into energy. Food into energy, right? We eat food. Food gets turned into energy. We're going to simulate this energy conversion in a fairly dramatic way. While that's heating up, let me go fishing here and see if we can get iron. Nail. Ooh, nail. Look at the nail.
It's got copper.
See here.
You got it?
There we go. Yeah. Cool.
What happened to our nail?
It's on in cardboard.
What color is it now?
It's the color of cardboard.
Yeah, it looks rusty, but it's not rusty. It's no, they were. Wait 1 second. That's too good. We'll see.
They might explode in fact. Please calmly direct yourselves to the edge.
I'm going to set this right here. So as we're leaving, you guys can come take a look at this to see how our reaction did. Now it's interesting because this was iron. It should have done about the same thing. There's a little bit of copper on a pillow. But the reason I don't think it worked completely goes back to that idea of, are we creating and destroying matter when we do a reaction? No. So we did the iron plus aluminum, iron oxide plus aluminum, became aluminum oxide plus iron. Where did the aluminum oxide go?
Turned into something really
It went
nice.
away?
It left in the pot.
It's still up in the pot? Or is it coating the iron? If aluminum oxide is coating the iron, can the copper get in there and react with the iron? It's still one. Okay? So, anybody ever drive a motorcycle? What do they put on the shiny parts of the motorcycle?
Chrome.
Chrome. Why do they put chrome there?
Shiny.
It's shiny and chrome doesn't corrode. Chrome doesn't react with the water and the oxygen in the air. Chrome doesn't rust. So you chrome plate, same thing when I talk about the nails, they galvanize steel. That's putting something on the outside of it that won't react with the water in the air. I was worried that nail was galvanized, obviously it wasn't, because otherwise it wouldn't have reacted. Okay? But this iron effectively has been galvanized with a coating of aluminum oxide. That's my theory. I haven't fully tested it. Okay, I need to get this to my motor.
Yeah, for us. Why is it on top of it?
potassium chlorate that we are melting down. I'm going to grab some gloves.
Bye.
One sec.
Bye.
Okay, we get that going so that we can add in our food, the Swedish fish.
How old are those fish?
Okay. You ready? Is there a reaction happening?
Wow, it's like electricity.
We put in food, mostly sugar. What's happening?
It's on fire.
It's being respirated effectively. It's becoming carbon dioxide and water. Same thing that happens in you when you eat food. Now, obviously, when it happens inside of you, it's a bit more controlled. But the principle is the same.
Wow.
That's one Swedish fish.
Swedish fish.
So that's how much energy you're getting.
Yeah, that's the energy you get from one Swedish fish.
Don't eat too much candy, kids.
Swedish
all at
fish
once.
for lunch.
There you go.
About
Not all at
30
once in your belly,
seconds.
but that's the process that's happening. You have enzymes in your body that can break it down, release energy. That energy gets used to convert into ATP. The ATP gets used to other kinds of stuff. Okay? All right, come on. Where's my...
Yeah.
Yeah. Woo.
It's like that food is soaking me out.
Yes, it's like excitosis. You're right, Aaron. Okay, what do I got left? Okay, this. It did freeze to the board. Look at that. That got me freeze to the board. I love it when it works.
Second time.
Okay, let me show you a couple other things here.
Yes.
Chemistry can be used for a lot of things. Oh, I think we're out of the last one here. This is cotton. Cotton's great for making what?
Clothes.
Clothes. What's one problem of making clothes out of cotton?
Burn. They also don't shed water as well.
Yeah, they don't breathe very well, and that happens. Okay, can't happen.
That's you inside there.
So you don't want to be inside of there. Okay, let's stick this.
You do that push applause here.
That out. Slugginess. Here. Now, chemistry can be used to make cotton
Not burn.
not burn, yeah. So we put that cotton there. And look,
It doesn't burn.
it's got a flame retardant on it, won't burn. That's great for upholstery, great for pajamas, okay?
I love flames.
So that's fire resistant cotton. That stuff's not going to burn, okay?
We can
That's
try.
pretty cool. That's pretty cool from a safety standpoint, pretty boring from a chemistry demonstration standpoint. But let me ask you this question. If we can make cotton that won't burn, what else should we be able to make?
Real
Fast
fast.
enough to explode.
Okay, now, I want you to look at my nose, okay? Don't look at the cotton, look at my nose.
Wow.
Now you can't see, right? It's like gone, right? Okay, look at my nose. Ready?
Wow.
Oh, gun cotton. Okay? There's nothing left, right? It's pretty much gone. Now, is it destroyed?
No, it's in the air.
It's in the air.
It's in the air. You see a little wisp of smoke there. Okay, it's floated away. It's
How much
in the
cotton
air.
have you breathed in your entire life?
How much cotton have I breathed? I don't know. I need to grab a spatula. 1 second.
Spatula.
Yeah, copper sulfate.
Yeah,
You kind of have it there. Now, the sulfate, did the sulfate participate in that reaction? Is there any sign of sulfur anywhere?
Did it build up to the stairs?
No, it stayed in solution. So can you have just positive ions in a solution? Can a solution be charged? No, a solution cannot be charged.
Go ahead.
So if you have positive ions, what do you also have to have? Negative ions. The sulfate of the negative ions. We call them spectator ions in that reaction because they don't actually do anything. They're just there to balance out the charge. So I've mixed together some zinc powder. Zinc is a metal. potassium chlorate or chloride, and some ammonium nitrate. Yeah, ammonium nitrate. We're gonna make a pile of this stuff right here on our counter platform. Okay. Somebody leave? Aaron. Who's going with Aaron? Where did Aaron go? Go grab Aaron if he wants to see this.
I think he's getting more water.
Well, water is important. What do we often use water for? From a safety, so we drink it. Obviously, we need to drink water. What else do we use it for? Putting out fires. Okay? Would you believe that I can start a fire with water?
Yes.
Okay. Aaron, you want to see this one? Let me go down to low
That's why I
power.
just came back fast.
Okay. Yeah, that'll work. So you guys can see this okay up here?
Yep.
I'm gonna squirt a little bit of water on it.
Wow, that's cool.
We just started a fire with water. Yeah, so some might sometimes with the byproducts of the reaction. Okay? And I know why you guys come to these things, right? Why do you come to these things? What do you really want to see?
Explosions.
Let's see explosions and flames, right?
Yeah.
I'm going to make what we call our
Booms.
giant purple flame.
What color is it?
What color do you think it's going to be?
Yellow.
Purple.
Here.
A giant purple flame.
A brown flame.
One more ready. Okay, like this.
That is very giant.
Not very giant like that anyway. Here, that light's off. Are you ready?
I think there's a reason it's lungs.
Definitely get the purple flame there, right?
Yep. Bottom, at the bottom is purple. You see at the bottom is purple and spice them
There's a
up.
lot of purple in there, isn't there?
Yeah.
That purple is coming around because of an element called manganese. It's actually from manganate, so it's an ion. So that purple color from the manganese. Now, who really takes advantage of the fact that different elements, when they get heated up, give off different colors?
Fireworks.
Fireworks is all about that, right? Bright red color, that's probably lithium or strontium. Bright green is probably copper. Bright white, like you get the sparks, those really big sparky ones. That is magnesium that we use to light thermite. Okay. And while we're here, I need to change over my fuel source.
Oh.
What's the difference between the fuel source?
Okay. Let's get this out. Okay. We've got one more balloon. So, like I'm using. What's burning? You know.
Fuel.
Natural gas.
Specifically.
Propane.
This is methane, it's natural gas, so we're hooked up to the city natural gas line. This is our natural gas, methane, okay? In that balloon I have what's called ethane.
Oh.
Ethane is a slightly bigger molecule than methane, has twice as much carbon and hydrogen. So what's going to happen? So I'm making a nice little flame here of my methane. What's going to happen if I expose the ethane to the flame? So we see? 3, 2, 1.
Wow.
Okay, come on.
Yeah. Woo!
Alright, I think that is pretty much everything I had. Really quick before we go, before I say you guys, I gotta clean up this mess. These are any questions. Now, let me give you an assignment, right? So next week, we're going to do some more work in your packets, alright? Now, what's the important thing about a merit badge? Who's supposed to do all the work? Yeah, not me, you. I've done a lot of work here to get you excited and get you started on this, okay? So we covered requirement, which one was it? 2A, about putting iron into a copper sulfate solution.
Do we have to write more about it?
And you can see what's happening here with our silver.
Oh.
Wow.
It's still growing.
That is cool.
Well, then come down here. Yeah, you need to talk about what happened and why. On the paper. That's what the paper's for. Okay? I don't know.
Can I see Dad?
Yeah, I'll bring it back. Maybe. There's actual silver there. Okay? So you guys, let me see your packet. So I want to give you some homework for next time, okay? And a lot of this stuff you can look up on the web. So I want you requirement 1 about safety equipment. We'll talk about that a bit next time. You can see something that I'm wearing right now. This is the safety equipment. Okay, so do that. Talk about safety and about pollution. And then we will do 3. We will do 4. We'll talk about 5 next time, the different divisions of chemistry. But I want you as part of homework to do requirement number 6 about government agencies that track chemicals. So there's a couple pages of stuff there. And I want you to do 7B, which is the one about different careers. So your homework. Take notes. You're going to send this out.
Okay.
Requirement 1.
David, take notes.
Yeah, secretary. Yeah, troop scribe. Take notes. So for next week, I want to see some work done on requirement number 1. Requirement number 6 and 7. So 1, 6, and 7. Okay, we've done most of 2. We'll finish up 2. We'll do 3 and 4 when we get together next time.
We have to do 2 now.
2 is what we did with copper sulfate.
No, we're right.
Yeah, that's what you're supposed to be doing all along. And who did not get a packet? So nobody knows packets to bring next time. You got the 1-page. Okay, I'll bring a full packet next time. So you can do that part there, and you can look online, find what the requirements are. I wasn't sure how many people were going to be here, so
One
David,
more,
you can look at
one more
John's.
for Evan, who is not here tonight.
Okay.
Yeah.
All right. So who needs a packet? Raise your hand. 1, 2, 3. About 3 more.
We could just can we just download them? We
Yeah,
can't.
it's just online. Just look up chemistry merit badge.
Okay.
Is it the second one?
Yes. Cu is copper, Fe is iron. That's the chemical equation, so you got to have that written down. Okay, anybody have any questions? I need to let you guys go home because you guys go tomorrow. No questions? You're all masters of chemistry?
Yeah.
Why don't we trust atoms?
They're in
Make up everything. That's right. Okay. All right.
Make
Thanks you
up
guys for
everything.
coming.
Fantastic. Everybody give a-
Yeah. Clap, clap. Woo-hoo-hoo.
So make sure you do some of that homework, and I'll see you guys next week. And those students more of this stuff.